Great, now we're on the last set of the videos. So we've talked about the systems, we've talked about distribution of fluids, we talked about regulation imbalances, and we also talked about electrolyte imbalances. Now we're going to talk about acids and bases and their imbalances. So the first thing we need to do is define what an acid and base is. Acids are hydrogen donors, where bases are hydrogen acceptors. When you talk about hydrogen with that little plus, it means it's charged. The best way to think of this is hydrogen. Here's a little hydrogen with a proton in the middle of it, and it has an electron floating around the outside. The electron carries a negative charge, and the proton carries a positive charge. While they're together, they neutralize each other, so they have no charge. But what happens when an acid donates a hydrogen, it lets the hydrogen leave without the electron. So the electron stays behind. Now you've got this hydrogen that's looking for an electron. It's desperate and it's angry out there floating around because it's looking for an electron to bind to. I always think of this, or I've used this example before, I think of this hydrogen as a little guy with a teddy bear. It's the only possession in its entire world. Something steals its electron and pushes it out the door. Now it's really ticked. It's bitter. It's angry. It's going to cause problems. It's like anybody with bad personalities. We call them toxic. We call them angry. We call them they have like a corrosive personality or toxic personality. It's the same thing with this hydrogen. Now, because the hydrogen has this bad attitude, since it's missing its electron, it's actually dangerous. It's toxic. It's corrosive. Right? A base accepts that hydrogen. So a base is something out there with lots of electrons that can actually accept the hydrogen and say, here, share my teddy bear with me. It makes the hydrogen happy and neutralizes the hydrogen. So that's the way I think of it. When we describe these acids and bases, we describe them as being strong or weak. If it's a strong acid, that means if you put it in water, it loses its electron quickly. So the electron's gone, this acid's free to start causing all this havoc and destruction. A base is the same way. If a base is put into a water and it's a strong base, that means it can cause damage too because it's carrying around way too many of these electrons. They're big, they're bulky, they're heavy, and it's angry because it's tired and exhausted and it just creates craziness. So acid and base can both be dangerous. Like this, hydrochloric acid. Where do you find that in the body? In the stomach. It's used to digest food, to help denature and change proteins. Okay? Sodium hydroxide, you can also find very, very small amounts in the body, but sodium hydroxide is a cleaning product that's very corrosive. Right? When we look at weak acids or weak bases, we describe them as weak because when you put them in water, they kind of just stay the way they were. They don't really break apart very easily, like lactic acid and carbonic acid. So let me give you an example of this on the next slide. Here's an example of a strong acid, hydrochloric acid. When I take this solution of water, we'll say this is stomach water, and then I dump hydrochloric acid into it, hydrochloric acid will come in, the chloride steals the electron and gives the hydrogen the boot. So now the hydrogen is wandering around angry. Look at all these free hydrogens. The more hydrogens you have in a solution, the more dangerous that situation is. It's hard to avoid hydrogen in here. And if the hydrogen gets you, it's going to destroy you. And then there are weak acids. So this is called carbonic acid. Carbonic acid's in the body all over the place. Carbonic acid doesn't break apart very easily, though. So the base side of it and the acid side of it like to stay together. They keep each other pretty happy. Right? Sometimes you get it where they go different ways, and sometimes you'll have a slightly acidic environment, but typically they stay pretty happy. That's weak versus strong. When we describe or explain how acidic an environment is, we describe it on the pH scale. And the pH scale ranges from 0, way down here at the most acidic you can have, to a 14, the most basic you can have, or the least acidic. 7, right down the middle, means it's no more basic than it is acidic. It's perfectly in the middle. When they describe this, it's actually called the Henderson-Hasselbalch equation, and it's a complex equation for figuring out acidity. But the inverse logarithm of the hydrogen concentration is the shortest explanation for how you get the pH. Let me break that apart for you. First, the inverse. Inverse means that something is opposite. Inverse means that the more acids you have that are free, more of these hydrogens floating around free, the lower the number is. So the higher the free acids, the lower the pH, and vice versa. The less free acids there are, the higher the pH. Log means that when you change a number by only one number, say go 7 to 6, log means you have to multiply it by 10, so by a factor of 10. And again, when you move it again from 6 to 5, you multiply it by another 10. So if you go from 7 to 5, you actually go times 10 times 10. You've changed this pH by 100, right? So you've changed the free acids by 100. Let me give you an example or let you figure this out. So your blood's right around 7.4. We'll say 7 just for math. Your stomach acid's about 2.0. How many more times acidic is your stomach acid than your blood? So hopefully you've started figuring this out. If I go from 7 to 6, it was 10 times. If I go from 6 to 5, it was times another 10. So from 5 to 4, times another 10. And I'm stressing in times. 4 to 3, times another 10. And then 3 to 2, times another 10. So if I just do this and just add zeros, like this chart does, if I go from 7 to 6, that's 10 times. Add another 0, 100 times, 1,000 times, 10,000 times, 100,000 times. From 7 to 2 was 100,000 times more acidic. That means 100,000 times more free acids floating in it. That's why your stomach is so dangerous. Remember, you're digesting other animals. If your stomach acids were to get on you, they would actually start digesting you. So why is that significant? Those little tiny changes, and the reason I put that example in is when you go from 7 to 6, it doesn't seem like much of a change, but in reality, you've multiplied the acid by 10 times. Why it matters? Primarily because of things like enzymes. When enzymes are in your body, they have a specific purpose. They're proteins with a purpose. If you change the pH by just a little bit, they don't work anymore. Since we're on the stomach has pepsin, which digests proteins, right? Pepsin's an enzyme that works at a pH of 2. When you get to the small intestine, well, something that normally works at a pH of 2, and you put it into a pH of 8, a million times different in acidity, will it work? No. That's why your pancreas actually has to release another enzyme to the small intestine called trypsinogen. It does the same thing as pepsin does. So trypsin will do what pepsin does, but they work at different pHs, and that's why it matters. So acid-base balance can also affect electrolytes. We saw this in the last video, especially with potassium. As you move potassium into the cell, potassium likes to kick hydrogen out. So now that free acid is going to rise in your bloodstream or in your interstitial tissue. Okay. And then it can also affect hormones. What always sticks in my mind is that a lot of hormones are protein-based. So you can kind of look back here. Enzymes are proteins. They get denatured. They don't work. Hormones can get denatured. They don't work. That's why eating certain types of hormones that are protein-based actually don't work very well because they get neutralized in your stomach, denatured in your stomach, and digested. So that's the significance. When you look at the absolute range of pH for your blood, you go from 6.8 to 8.0. These are extremes, and it may not seem like very much. 1.2 is the difference, but remember, there's a 10 times acidity difference between those two numbers. So your ideal pH is 7.4, and this is described by systemic artery blood being closer to 7.45, systemic vein blood 7.35. And the reason I'm stressing those is because what's the difference between these two bloods? Arterial blood, system arterial blood's higher in oxygen and lower in carbon dioxide. When you see carbon dioxide, you can always assume that hydrogen's hanging out with it. So if I have more carbon dioxide in a part of my body, I'm going to have more acid in that body. If I have less carbon dioxide in that part of the body, I'm going to have less acid, more basic situation. So of these two, which one's more acidic comparatively? Right, 7.35, it's a little bit lower on the pH scale. So what would you expect to happen here? Would you have more or less CO2 in here? You'd expect more. It's more acidic. Okay? This is slightly more basic, where this is closer to the acidic range. Okay? Acidosis and alkalosis are two terms, and we describe them as if you go below 7.35, you're too acidic. If you go above 7.45, you're too basic or alkaline. If you go to the extreme ranges that I was talking about here, anything beyond this leads to death. Where do the acids come from? So acids come from basic life processes. When you eat food, you break the food apart, and some of that food turns into acids. It just happens. And I'm going to give you a question in just a slide that's going to have you look this up. But those acids can get into your body, and they can change your pH. Once those nutrients are in your body, processing them to make energy out of it. So when you eat a sandwich, you have to break it down from big structure like proteins into little amino acids, and then those amino acids can be stored, and then later you pull them out, and you can turn amino acids into energy, like ATP. You can take fats and turn them into energy, like ATP. So for instance, if I'm burning lots of fats, I can make ATP, but I make these byproducts, like ketone bodies, which are also known as ketone acids. So these ketone acids can accumulate in my system, and as they're accumulating, they make my blood lower in pH, more acidic. Another one's enzyme activity. Anytime you see an equation like this, you want to imagine a bathtub under it. And I'm going to tell you why, because this is an important equation. If you add something to this side of the bathtub, what happens to that stuff on the other side? Does the water just sit on the side of the bathtub? No. It distributes across and evenly spreads. When you take an equation like this, if you imagine it has walls on it, and you add to this side, this equation will slowly drift over and make more of this, and then slowly drift over and make more of this. What if I pull the plug over here? What if I pull the plug here and I drain this side out? Does the water stay high on this side? No. The water will shift, or the substance will shift over here to make more of this, and then leave the plug. The reason I point that out is because we're going to use this equation again over and over for how you regulate acids and bases. So in this equation, if I hold my breath, I accumulate CO2. This equation shifts this way, and what do I build up? Free acids. Lots of free acids. If I have too many free acids, how can my lungs get rid of these acids? Well, my lungs can blow CO2 out, which brings those acids across this equation and then out of the body. So it's important to know where the acids come from. Speaking of which, next question. So question number 8. So you're going to look up, use the internet, what effect does Atkins diet have on the pH of blood and urine? Remember, you want to use reputable sources, so don't go to the Atkins website, because they're going to tell you all kinds of good news. All right, everything's going to be perfect. You want to look at some kind of a .gov, .org, some kind of an education website, and find out what happens to the pH of the blood and the urine as a result of the Atkins high-protein diet, which you might want to put in your explanation. So what is it about that high-protein diet that changes the pH? Go ahead and hit pause, write it down, and then come back when you're ready. Okay, one last thing on pH. We described strong versus weak, but we can also describe acids as being volatile and non-volatile. Volatile acids change quickly is the best way you can think of it. They change extremely fast, so they can be eliminated really fast. In the lungs, think of it, you're breathing constantly in and out. You can take this thing called carbonic acid, and you can turn it into CO2 gas and blow it out really quick, in milliseconds. Non-volatiles, those things don't change very easily, like sulfuric acid or phosphoric acid. These are pretty acids that like to stay in the state that they're in. They don't like to change. So typically, your kidneys are going to have to get rid of those. And I'm kind of saying this now because I'm hinting or winking towards the future. The next thing you need to know are how you buffer or you stop or you eliminate acids and bases. There are really 3 lines of defense against hydrogens or acids. The first one's called the chemical buffer, and this works immediately, within seconds, and I'll explain the different types. The second one's called a physiological buffer system, and it can actually be subdivided into 2 parts. So you have chemical, and then you have respiratory and renal. So they're your 3 lines of defense, either the chemical buffers, or the lungs, or the kidney. And here are some pictures from your book, which I'll walk through in a few seconds. Right. So the chemical buffers first. First chemical buffer, what a buffer is, actually I should probably cover. Buffers are anything that can neutralize a weak acid or a weak base. Buffers like to keep the pH consistent. So if I have this perfect pH of 7.4 and I add a little bit of acid to it, buffers are weak bases that neutralize it. Or if I have this pH of 7.4 and I add a little bit of base to it, these weak acids are buffers that neutralize them so that the pH stays consistent. And this is really important in the blood because remember, you want to stay at 7.4. Anything beyond 7.35 or 7.45 is considered acidosis or alkalosis. Right? So these buffers can also take a strong acid and make it a weak acid. It can neutralize weak acids or take a strong acid and make it weak. So when you add acids to an environment, in other words, it just makes smaller pH changes, keeps it more safe. Right? The amount of acids and bases can be flipped around to manipulate the situation easily. To make something more acidic, you can either add acids or you can take bases away, and it does the same final result. To make something more basic, you can add bases to it or you can take acids away, and you get the same final result. So next is called the bicarbonate buffer. So a bicarbonate buffer, this uses actual bicarbonate, the chemical, to buffer. So common structures you'll see are something called sodium bicarbonate or carbonic acid. And right in between you have bicarbonate. Right? It's the most important buffer system in the body. And when you look at it, it's outside the cells, and it's typically a transition between kidneys to lungs, cells to other cells. Right? So it buffers things. It takes a strong acid and neutralizes it. So this is acidic, this is basic. You have both of these. So if an acid comes along, it goes to the base and gets neutralized. If a base comes along, it goes to the acid and gets neutralized. But you're trying to maintain a perfect ratio, or 7.4 in the blood. We refer to this ratio as being 20 to 1, which means for every 20 bases you have 1 acid. If that falls outside of that range, you have problems. So ideally, you're going to keep about 20 bicarbonates around and 1 base around, or sorry, acid around. So this is carbonic acid. When that range falls back and forth, you start falling into disorder. So I love these teeter-totter examples throughout the next several slides, but here you can see bicarbonate and you can see CO2. What does the CO2 represent? You start accumulating CO2, you're accumulating acids. So as this side starts getting heavy, it starts going and shifting over to the acidic level, closer to 7.2. Bicarbonate buffer comes in and it neutralizes the acid, brings you back to normal. These chemical buffers are really fast buffers. They work really, really quick. Right? Another one's the phosphate buffer. So phosphate buffer, phosphate's a base. It grabs a hold of the acid, neutralizes the acid, and escorts it out of the body. It's a pretty simple process. So you can see, here's that equation, CO2, H2O, carbonic acid, makes an acid, makes bicarbonate, takes the acid, pushes it into the nephron, and then phosphate will grab a hold of it, escort it out of the body, and then leave it out there. Protective. And then the last of the chemical buffers is protein buffer. And the best example of a protein buffer is actually hemoglobin. These protein buffers are inside cells, intracellular. So the hemoglobin is in here, and the hemoglobin can meet up with an acid and neutralize the acid, and hold on to it. So if a red blood cell, as an example, has acids in it, the hemoglobin will bind to the acid, hold on to the acid. The bad thing is that when the hemoglobin is holding acid, it can't hold oxygen, which we'll get to when we talk about respiration. But the more acidic the environment, in other words, the harder it is for you to carry oxygen. So another problem with acidity and basic imbalances. Right? But when you look at proteins, proteins are interesting because proteins have an amine side, which is a base, and they have an acidic. So a carbonic acid or carboxyl group that's acidic on the end of it. So that no matter which side of the protein you look at, one of them is going to help neutralize either an acid or a base. When you put a whole chain of these together, they're like Legos. You still have a bottom Lego that's a base, top Lego that's an acid. Stack more on, you still have a bottom Lego that's a base, top Lego that's an acid. So they're always prepped and ready to neutralize. So if we take this equation that we saw on, 2 slides ago, and you start making lots of these acids, as long as they're inside the red blood cell will bind them to this hemoglobin and neutralize them. See, no charge left. If the chemical buffers don't work, the next system that's going to take over is your respiratory system. So if you start accumulating acids in your blood, the next thing you know, your respiratory system is trying to blow out what? CO2. As long as it blows out the CO2, it's going to shift, oops, I don't know how this equation got shifted over, but it's going to shift the acids over here and leave. So you get rid of acid by blowing out CO2 because the acids are volatile acids. They change quickly. This carbonic acid, okay, it doesn't work on the fixed acids, the non-volatile acids. It only works on things like carbonic acid. Right? And then the last thing, if the respiration didn't work within minutes, then within hours to days, the kidneys will have to do the job. And the kidney has lots of mechanisms that are going on to help get rid. So the kidney's kind of cool because it can get rid of acids, but it can also get rid of bases. It can also bring back in bases. So the kidney is an important structure for helping maintain pH. And then there's some other ways that your body buffers, like just moving the acids around. Like when we talked about the hydrogen and potassium, it didn't neutralize the acid, it just shifted it to another compartment, so it wasn't such a problem. So let's talk about the acid-base imbalances. So when we talk about being below 7.35, remember what the situation is. Is it acidosis or alkalosis? It's a lower number, so it's got to be the acidosis. Here's that whole system again. This is the Henderson-Hasselbalch equation. And when you look at this, it shows you. Here you have bicarbonate, which is a base, CO2 that's associated with an acid. When you look at the proportions, you should have 20 bicarbonates, 1 acid. When I look at this, I always think of a math equation. If they say the ratio needs to be 20 to 1, I just do the math. That means it's going to be 20 naturally. So 20 divided by 1 equals 20. If they say that your ratio drops below 20 to 1, that means your outcome is lower than the number 20. If the number ever falls below 20, it's an acidic state. There are 2 ways to do that. So if this is a base, if the base reduces, we'll say it cuts in half. You're no longer at 20, you're at 10 to 1. Your number, your outcome, 10 divided by 1 is now 10. It's a state of acidosis because you lost bases. But what if the opposite is true? What if I start gaining acids and I turn this to 2? Well, 20 divided by 2 is still 10. It's below 20 as an outcome, so it's still acidosis. The good thing is it's quick to figure out. You can figure if it's acidosis or alkalosis. But the problem is that there are so many possible causes now that you don't know what caused it. You just know the state that you're in. Right? But these bicarbonates and carbonic acids and CO2, they can all shift around as long as they're kept in balance. They're like fighting on a teeter-totter, and they're all trying to keep it perfectly level. We can describe what's getting out of control by the pH. Is it the acids or is it the bases? And I've already talked about this a couple times. Right? If we talk about the ratio changing, we're talking about that 20 to 1. For every 20 bases, you need 1 good acid. And I like this chart, and I put it on the next slide for you, so if you wanted to print it out, you could. But it shows, here's your teeter-totter. This is a big pile of bases over here and a little pile of acids over here. Well, it doesn't seem right that it's balanced because let's say you have a pound of feathers over here. They take up a lot of space. Where you have a pound of lead over here. Which one's heavier? They're the same. They're perfectly balanced. Okay? So the lead, of course, if I add just a little tiny drop of lead, it's going to make a big difference. But it's going to take a bunch of feathers to make a difference. So in other words, the base, if your bases get out of control, it doesn't take much before they cause damage. Or sorry, acids. But the bases, you have to have an extreme situation. So here's the next rule or principle you want to say. Abnormal CO2 changes, CO2 associated with the lungs, so we say it's a respiratory cause. So if you have too much CO2 in your blood, you have too many acids in your blood, what's the problem? Acidosis or alkalosis? It's acidosis. If it's because CO2 changed, we know it's the lungs' fault, so we call it respiratory acidosis. Anything that's not respiratory is metabolic. When there's a change in this bicarbonate here, it's metabolic in nature, period. You can't point your finger directly at the kidney or any other organ right now, but you just know it's not the lungs. Let me give you some examples. So you can see, in this situation, respiratory did it. That means CO2 has changed over here. In this situation, you gain CO2, which means you gain acids. You start going into an acidic state, 7.1. Right? It's because of the lungs. It's respiratory acidosis. Over here, you lost CO2. So when you lost CO2, the base became more powerful, and you start going up into the 7.7 range. You're going into alkalosis. But it's because of a change in CO2, so it's respiratory. And then metabolic is just the opposite. If it has anything to do with bicarbonate, but the CO2 is normal, then you know it's metabolic in nature. If you lose bases, the acids get heavier, 7.1. You're in metabolic acidosis. If you add lots of bases but didn't change the CO2, it's still bicarbonate, it's metabolic, but when you look at the pH, it's 7.7, so it's metabolic alkalosis. That's just an overview. So now, acidosis and alkalosis, what are the typical signs? The way I usually look at this is the organs that show the fastest changes are going to be the ones that use electrical communication, like the brain, the heart, and the muscles. And especially the brain, because you can test that without having special devices. You can talk to the person, ask them questions. So in acidosis, I think electrical activity depends on proteins being in the right shape, and it depends on those proteins sending signals. If I introduce lots of acids, I start changing the shape of those proteins. I can't get action potentials anymore. So what happens to my thinking? What happens to my communication with my muscles? What happens to my thought process? What happens to my breathing? All these things that are controlled by neurons start slowing down. So you see things like generalized weakness. You see disorientation, confusion. They get really tired. They slip into a coma, and if it's not corrected, they'll die. Right? So signs of acidosis are typically CNS depression, decreased synaptic transmission. The other way to look at this, and weakness of muscles, is what about alkalosis? Well, if acidosis slowed down the nervous system, what's alkalosis going to do? It's going to overexcite the nervous system. It needs to go really quick. It makes you have these abnormal, like anxious feelings, this numb tingling feeling. You know, when you cross your legs for too long and then you uncross them, that weird tingling? Those are neurons that are firing like crazy. You got this weird sensation. They're overexcited. When you blow up a bunch of balloons and you lose carbon dioxide, now you're in an alkaline state because you just lost acids. You feel lightheaded. You feel tingly. You don't want to just sit down and take a nap. You feel weird. And at that point, if you sat down, you just sit there feeling really dumb and silly, right? If you ever had that happen before where you try and blow up too many balloons, you don't pass out. You sit down and you're like leaning and you know people are looking at you funny, blah, blah, blah. It's an anxious feeling. So you get nervous. You get little muscle twitchiness, spasms, convulsions. And unfortunately, if this happens to respiratory muscles, it could lead to death. So general rule of thumb here is acidosis depresses the central nervous system, and you see signs that are related to that. Alkalosis irritates or increases nervous activity, and you see signs accordingly. Right? Compensation. So now we figured out what breaks. If the lungs break, you need to depend on the kidney to fix it. If the kidney breaks, you need to depend on the lungs to fix it. If you have metabolic acidosis, here's the trick. If it's metabolic, it's anything but the respiratory. Does it have to be the kidney that's broken? No. So compensation is talking about fixing those problems. Lungs will try and compensate by blowing out what chemical? CO2. Renal will try and compensate by modifying acids or that chemical bicarbonate. But together they work in this nice, tight little fashion where they keep everything moving perfectly. Right? So when you think about compensation, it's trying to fix an acid-base imbalance. You've got all these chemical buffers, you've got the kidney, you've got the lungs, and they're all trying to maintain homeostasis. If the lungs are not working and you accumulate CO2, you'll buffer it with chemicals, but that can only last for so long. Then you start accumulating acids, it's going to be up to the kidney to start excreting them, to get rid of those, urinate them out. And the whole goal is to maintain homeostasis. If the lungs are breathing too fast and they're blowing out CO2, what happens to your acids? They leave. When the acids leave, then you become too alkaline. The kidneys, at that point, are going to stop. They're going to quit getting rid of acid. They're going to try and help you hold acid in your body. Then they're also going to make bicarbonate and push it in. And the bicarbonate, if you're holding in CO2, they make bicarbonate and neutralize it. If you're blowing out the CO2, then they're going to start retaining the acid, and they're going to try and excrete the bicarbonate. Sorry, I had a little flaw there. But the pathway kind of explains itself. Right. So here's respiratory acidosis. Don't know why that did that, but there you go. When you're doing respiratory acidosis, you can look at it two ways. Either the pH is under 7.35, or the ratio drops below 20:1. If it's respiratory, what chemical does it have to be because of? CO2. So you want to look at a cause that has to do with the lungs. Hypoventilation. You're not blowing out CO2, so you're accumulating in the blood. How can you compensate? Remember your three lines of compensation. You have chemical. So what's the body going to do? Is it going to free up more acids, or is it going to neutralize them? It's going to neutralize them. It binds to the hydrogens to keep them from being so dangerous. If the buffers don't keep up, then you depend on the second line of defense, which is the respiratory. The respiratory is broken, so can it do anything right now? Nope. It's broken. So what organ, the tertiary line of defense, is going to have to kick into effect? The kidney. What can the kidney do? If it's acidosis, what will the kidney do to acids? It'll try and excrete more. It tries to push out more. What would it do to bases? It'll try to keep more bases. So the kidney does two things, and you have to keep that in mind. If you become too acidic, the kidney can get rid of acids and keep bases. If you become too basic, the kidney will try and get rid of get rid of bases and keep acids. So here's a little slide I thought was pretty cool. It's a mixture of your book over here and a picture I found that was kind of cool. But you see respiratory acidosis. These people, they're not breathing very well. The CO2 is building up. Some diseases you might want to associate with respiratory acidosis would be emphysema. They can't get the CO2 out. So the CO2 accumulates in their body and causes an acidic environment. Right? Anything that prevents you from getting air out and CO2 out is going to cause acidosis as respiratory. Just the opposite, respiratory alkalosis. What happens to your breathing? Actually, let's take it one step at a time. The pH goes above 7.45, and it's because of CO2. the ratio goes above 20 to 1. So how can you, or what would be a cause? If hypoventilation caused acid to build up, what's happening to your ventilation now? Too much. You're blowing out too much CO2. You're losing the CO2, which means that your pH is rising to an alkaline level. Your chemical buffers are going to do what to your acids? Are the chemical buffers going to bind to the acids in your blood, or are they going to free them up? They're going to free them up. They free them up to try and neutralize these bases that are out of control. Your lungs are the cause. Can the lungs fix it then? Nope, the lungs won't do anything. They're broken. So what organ has to kick in? Right, the kidney. What's the kidney going to do to acids? Will it keep the acids or get rid of the acids? The kidney will try to keep acids. Right? What will it do to bases? The kidney will try to get rid of bases. It kicks them out. So it conserves the hydrogen and excretes the bicarbonate, the base. And here's a little slide that shows some of the symptoms. So just remember, alkalosis and acidosis, the symptoms are going to be very similar. So in alkalosis, remember, you're going to be a little bit jittery, a little weird, you feel lightheaded, you feel a little anxious. Right? With acidosis, you feel depressed, you feel sad, you feel like you just want to lay down and take a nap. Metabolic acidosis means it's not the lungs. Acidosis is telling you what happened to the pH. It dropped below 7.35. What happened to the ratio of 20 to 1? It went lower than 20 to 1. Right? And in this situation, it's because of bicarbonate. Right? So some causes: diabetes mellitus. Diabetes, you build up things like ketone bodies or ketone acids. Strenuous exercise that leads to lactic acids. Another common cause of metabolic acidosis is GI related. Where do you think it's going to be? Will it be because you're losing stomach acids or because you're losing bases from your large intestine? So if you lose bases from your large intestine, the acid stays behind and causes acidosis. So diarrhea would be another good example of metabolic acidosis. Compensation, the chemical buffers, what are they going to do to the acids? Will they free them up or bind them? They bind them. Can the lungs do anything about metabolic acidosis? Absolutely. What are the lungs going to do to help get rid of acids? They're going to blow them out. So these people start breathing deeper. They're trying to blow out that extra carbon dioxide because it will take acid with. And then metabolic acidosis. As long as the kidney is not broken, the kidney can help fix this. What will the kidney do to acids? It'll try and get rid of them. You'll urinate out acids. What will the kidney do to bases like bicarbonate? It'll make new bicarbonate and bring it back into the system. And then here are some of your symptoms. So metabolic acidosis, again, what's going to happen is these people start breathing more. They're trying to compensate. They're trying to get rid of those acids that are building up in their body because of metabolic functions. And then some of these causes we'll actually talk about in just a little bit. Right? Other causes. And then metabolic alkalosis. So it doesn't have to be the kidney, but it's definitely not the lungs. So what you're going to look at first is the change is going to be based on which of these two chemicals, CO2 or bicarbonate. It's because of bicarbonate. So the bicarbonate pH will go up 7.45 and above. What happens to your ratio of 20 to 1? It goes above 20 to 1. It's because of bicarbonate. So some causes: vomiting. When you vomit, you lose lots of acids, and the blood just keeps giving more acids, and you lose more. So you just become a lot more and more basic because you're losing your acids. Another cause can be taking in too many alkaline foods or drugs. So taking in a lot of bicarbonate-rich foods, baking soda-rich foods, or taking in drugs that are coated with an alkaline coating, too many of them. Right? So how does your blood compensate? Your chemical buffer is going to do what to acids? Will they bind them or free them up? You have too many bases, so they free up the acids. Can your lungs work here? Yes. So your lungs are going to start doing what? Breathing heavier and blowing out CO2, or slowing down the breathing to hold in CO2? It's alkalosis, so you're going to try and keep the acids. You're going to hold in CO2. So you'd see their breath slowing down. And as long as the kidneys aren't broken, can the kidneys compensate? What can the kidneys do to these bases? The kidneys can urinate out the base and try and do what with acid? Try and keep the acid. So conserve acid and get rid of bases. All right. So there's the signs and symptoms, and you can see the vomiting, nausea, diarrhea can cause it. Here's another summary slide. So here are your 4 categories. They're all 4 teeter-totters and their causes. And then winding down, so how do you determine the pH of somebody's blood? You take something called an arterial blood gas, so an ABG. When you look at that, there are several things it measures, but here are the 3 primary things you're gonna look at. You're gonna look at their pH first, and then you're gonna look at their CO2 partial pressure and their bicarbonate. So when you look at the pH, 7.35, is that going to be okay for an artery? Yeah, that's okay for an artery. If it goes below 7.35, you have what? Acidosis. If it's above 7.45, you have alkalosis. So you look at the pH first, and it tells you right away, do you have acidosis or alkalosis, or are they normal? Next, you're going to look at these 2 chemicals. So the CO2, the normal range for CO2 is 35 to 45. So let's say the pH is 7.25, which is low, really low. And I say that it's respiratory caused. What would you expect to happen to the CO2 in their blood? Would the CO2 be low or high? So it's acidosis, so they have too much acid, which means they're also going to have too much of CO2. If it's respiratory acidosis, you can see right away that the CO2 goes up. Okay? Sometimes you look at this and it'll be like 7.3, but they'll have really low CO2. Does that make any sense? Being acidic and having a low CO2? If that happens, that means what's the cause? You need to look at the bicarbonate. Okay? So it's an acidic environment. What you'll probably find is that it's low bicarbonate. So why was the CO2 so low? It's because the lungs are trying to fix the metabolic acidosis. So the lungs are trying to fix that. It's kind of like a 3-step procedure. You look at the acid first, and with acidosis, you either know it's going to be high CO2 or low bicarbonate. Whichever one matches your prediction, that's the cause. If it was low bicarbonate, if it's low both of them, but it's low bicarbonate that causes acidosis, you know right away it's metabolic acidosis. So you're going to see oxygen when you look at these ABGs too, but the oxygen doesn't matter because the oxygen is not affecting acid and bases. You're looking specifically for the pH, which those letters are switched around, but you're looking for the CO2 and you're looking for the bicarbonate levels. Right? You look at the oxygen when you're looking for things like hypoxemia or hypoxia eventually. So here's a nice little chart that helps summarize. So look at the arterial pH first. Is it below 7.35? Because then it's acidosis. Then you look for which one's a problem here. Right? And then is it above 7.45? Then it's alkalosis. And look at your bicarbonate and look at your CO2. Right? So you can take a step-by-step diagnosis when you're figuring this out. I put a couple review slides that walk all the way through, that kind of walk through the pathophysiology too, like how diabetes can affect metabolic acidosis. Right? And the last thing I'm going to talk about is the anion gap. And I'm not going to spend a ton of time making you calculate the anion gap, figuring it out exactly how it works and all that. But the significance you need to know is anion gap, when you have a metabolic situation, not respiratory, but metabolic, it could be anything that's not the lungs. The anion gap helps you distinguish what's the problem. So when we look at all of the ions, so we have sodium, potassium, chloride, bicarbonate, plus we have these other things, which we usually call A minuses, which mean anion proteins. Okay? When you take all of these into an equation, you'll come out with a number that's roughly about 10 to 12 milliequivalents of some other miscellaneous. When this number starts changing, getting too high or too low, then you know where to look. Are you looking for a cation or are you looking for an anion? And there are a lot of other things, like lactic acid. It's not measured. It could be the other. So it could be lactic acid that's causing metabolic acidosis. It could be ketone acids. So ketone acids aren't measured here either. That could be causing the other. right? So in general, anion gap, it's just there to help you diagnose what type of metabolic disturbance it is. So examples like diabetic ketone acidosis affects ketones. Salicylate poisoning is usually associated with things like, salicylate is in salicylic acid, which is aspirin. Okay? Lactic acidosis, which you could probably predict one of the problems that could cause that. Renal failure could cause an imbalance of all types of different things. So it helps narrow it down. Here are the four main causes of anion gaps. And there could be more, but these are the four main ones. So ketone acidosis, or diabetic ketone acidosis, uremia, lactic acidosis, and toxins. Things like ethylene glycol, which, by the way, is having a brain fart. It's the stuff in the front of your car. Antifreeze, that's the name of it. Methanol is wood alcohol, is what they call it. Back in the old days of moonshine, if they improperly made their alcohol, their ethanol, it would actually turn into methanol, and it would make you blind. Okay. Formaldehyde. Formaldehyde is actually used as a medication to treat certain disorders, like psychological disorders, and not even psychological, but even convulsions in the brain. And the salicylate, I already told you, was in aspirin. So here are some different examples of things that aren't measured normally that could cause acid-base imbalances. And I'm not going to make you do the measuring. But I am going to have you look these up real quick. So here's your homework question. How do you get those three things? How do you get DKA? How do you get salicylate poisoning? And how do you get lactic acidosis? A pretty simple question. You can use the internet to find that out, but just make sure you explain kind of the pathophysiology. So with DKA, what's changing that leads to a buildup of ketone acids? I'm giving that away, which leads to acidosis. And then I put in here how you break things down. So, like I said, the three-step process that I was talking about before, here's the three steps. Look at the pH, look at the CO2 or the bicarbonate, right? And then look at the opposite to see if the body's compensating. So before I said you had a pH that was 7.3. You know right away it's acidosis. If you look and both of these are low, that means that what would you suspect to cause acidosis when it's low? When CO2 is low or when bicarbonate's low? The bicarbonate. So right now you know it's metabolic. But if the CO2 is abnormally low, that means the lungs are actually compensating and trying to fix that. Right? So they call that compensation. You can actually determine whether the lungs are doing their job to catch up. So if you saw 7.3 pH, you saw that the bicarbonate was low, but you saw the CO2 was in normal range, their lungs aren't keeping up. Their lungs aren't compensating yet. So it's just a three-step process, like I said. So here are a couple of fun questions. You can look, here are some normal values. So pH should be 7.35 to 7.45. Your oxygen is about 80 to 100%, or parts, sorry. And then your CO2 should be between 35 and 45, and your bicarbonate should be between 22 and 26. So these are the normal values. And this is talking about the blood, or sorry, oxygen in the blood. So this is your hemoglobin saturation is what it's talking about. So are your hemoglobin 100% saturated? Are they 95, 90, 80, whatever? So it tells you it's low. For acid-base, remember, you don't need these two values. You're looking at these three. So if we were to give you an example of this, a patient is in intensive care because he suffered a severe myocardial infarction 3 days ago. The lab reports give the following examples of an ABG. It says the pH is 7.3. What do you know already? Acidosis. What would you expect to happen? Would you expect for acidosis? Would you expect there to be a low or a high CO2? You'd suspect it could be high. And then after you know that, would you suspect that it would be high or low bicarbonate? Well, if it's acidosis, you'd probably expect it to be a low bicarbonate. Which one is actually low here? Look, the CO2 is low. The CO2 is low. It's telling us that this person has respiratory. Remember, because if it's sorry, I said that wrong. The bicarbonate's low, so you expect it to be metabolic. The CO2 is low too, so what's this person's body doing? They're compensating. So if both of these are low, it's metabolic acidosis, and the body is compensating. There's kind of a neat little chart. Oops, there it is, metabolic acidosis with compensation. There's a neat little chart that you can actually see where things are at. So if you look at the pH, the higher the pH, you're in the alkalosis range. The lower the pH, the acidosis range. If you look at the concentration of bicarbonate, if you have metabolic acidosis, you'd see a lower amount of bicarbonate. If you see respiratory acidosis, then you see a higher amount of bicarbonate because it's trying to compensate. And then the same over here. So you can kind of watch the shifts. It's a neat little game. Some people just use this little chart to help remember. Right, so how about this one? The blood pH drops 7.3. How's the body going to compensate? Right, just in general, what would you expect the body to start doing? Well, fastest way to compensate would be to breathe. So you start seeing the breathing go faster. The carbon dioxide is going to start leaving a little bit quicker. Right? How about the pH increases to 7.45? How's the body compensate? What's going to be the fastest way the body compensates? Slow down breathing. Right? So you've got a lot of these little pieces of information. You take one point at a time, and then you can actually look at the next one and say, well, now that I know it's acidosis or alkalosis, are the lungs working? If the lungs seem to be compensating, then you know it's going to be the opposite. It's going to be like a metabolic cause. So in this one, if their pH is 7.45 and they're breathing slowly, they're actually compensating for what? Metabolic alkalosis. So here's your last question for the homework assignment. So Mike's taking narcotics for pain. His breathing rate has been depressed as a result. What will happen to his blood pH and how will it compensate? So answer that, and then what would you expect the values to be? And it doesn't have to be a specific number. It's just a range. So look at the ranges for normal and then type what you predict. Right? All yours. I'll talk to you on the flip side.